In the mid-90s, space explorer Robert Williams was about to take what his colleagues considered a very unwise step. He wanted to point the Hubble telescope for 100 hours at a part of the universe where there were no even remotely notable objects. Other astronomers thought this was an irrational waste of resources and time for such a valuable research instrument. However, Robert Williams did it his own way. He was the director of the Scientific Institute and could freely allocate 10% of the telescope's observation time. The researcher promised that if he didn't find anything interesting in that area, he would resign from his position. So from December 18th to December 28th, 1995, the Hubble telescope began observing the area near Ursa Major. That's just 1/30th of the width of Earth's satellite. As a result, we obtained 342 images of this area. It turned out that there was a huge number of galaxies in this area. Their number reached 3,000. Some of them were as old as 12 billion years. Galaxies of completely different types were observed, both elliptical and spiral, blue, orange, red, yellow. The image with the diverse galaxies began to be called the Hubble Deep Field. This discovery became a real miracle. Hubble. It wasn't the end. The research continued. Scientists wanted more data about this area. Almost 30 years later, the James Webb Telescope took on this mission. The first part of James Webb's mission began in the middle of 2022. For a long time, the device was searching for galaxies in the early universe in separate fragments of the vast cosmos. Scientists expected images of deep field variations similar to Hubble's, and no one expected that this time they would be able to find something extraordinary. However, the result exceeded all expectations. The researchers immediately recorded galaxies that formed just 200 million years after the Big Bang. It could be confidently stated that the James Webb Telescope has lifted the veil of mystery from a previously little explored period in the development of the universe. Nevertheless, these galaxies had features that scientists did not suspect. The brightness of these objects was very high. They contained a number of stars equivalent to billions of solar masses. Galaxies of such enormous sizes do not fit into our understanding formed by the standard model of the universe's development. Did scientists make mistakes in the past, or is there another explanation for what James Webb discovered? And most importantly, do the discovered data disprove the Big Bang theory? To have a complete understanding of the situation, let's delve into earlier judgments about how the universe was formed. During the first second after the Big Bang occurred, the four fundamental forces separated from each other. These are gravity, electromagnetism, as well as the strong and weak nuclear interactions. At that time, the universe was a hot mixture of primary particles. After that, during the next 3 minutes, the temperature of the cosmos decreased and expansion was taking place. That's when helium nuclei formed, along with other fairly light elements. 400,000 years later, the universe had cooled enough for the first atoms to form. The first stars appeared 150 million years later. These were massive stars that we call population 3 stars. They were composed mainly of helium and hydrogen. Clouds of gas and the first proto-galaxies formed around such stars. They interacted with dark matter. Through gravitational interaction, these galaxies merged into a single whole and formed larger galaxies. All of this happened over the course of about 1 billion years. As we've already mentioned, the data obtained from James Webb calls this version into question. Scientists claim that we would have detected a huge number of parts of protogalaxies that have not yet merged with each other. However, we observe objects that can be considered large galaxies. We include GLZ, 13 among such galaxies. Its redshift is 13.1. Redshift is a parameter by which we determine how much the universe has expanded. The greater the redshift, the higher the speed at which the object is moving away from us. We have detected galaxies with a redshift greater than 11 extremely rarely. The Hubble telescope found one such galaxy during its mission. It's a different story with James Webb. Since it's an infrared observatory, the device can explore more distant regions of space. Looking at the redshift value of GLZ 13, the galaxy formed within the first 300 million years after the universe began. Initially, redshift was observed photometrically, meaning with the use of different color filters. The data from such observations could be inaccurate, especially regarding the exact value of the redshift. Observations using the Atacama Large Millimeter Array showed that the galaxy does indeed have a redshift, but its value is about 13. The mass of GLZ 13 is 1 billion solar masses. This goes against the generally accepted models of star formation. If all available components participated in star formation, the size of this galaxy would not be so enormous at such an early stage. Even if we assume that stars formed so quickly and increase their mass so rapidly, then why don't we see something similar in modern galaxies? It's quite difficult to logically justify this based on the generally accepted cosmological model, lambda cold dark matter. As you can see, here, lambda stands for dark energy, and cold dark matter stands for cold dark matter. Scientists are trying to explain the data obtained by James Webb using one of the cosmological models, for example, the lambda cold dark matter model. Some researchers claim that the accumulation of huge masses during star formation is characteristic specifically of the early universe. The gas pressure and temperature are at a high level. These factors influence how star formation occurs. There is a theory that magnetic fields also formed earlier than previously thought, and it was their influence that accelerated the movement of particles, which resulted in such efficient star formation. The researchers have another hypothesis as well. It is quite possible that the brightness of the galaxies is so high because in the early stages of the universe, the amount of cosmic dust was minimal. The data from James Webb can also be integrated into the rather controversial idea of modified Newtonian dynamics. According to this model, dark matter does not exist, and the probable traces of its existence can be explained by gravitational fluctuations. There are aspects in Webb's observations that can be explained using this model rather than lambda cold dark matter. Although the telescope has detected galaxies whose existence contradicts generally accepted cosmological models, this does not invalidate the Big Bang theory. This theory was created based on a huge amount of observations. We can't just disregard their existence. For example, the Big Bang helps us find out how much of each element existed in the universe in its early stages. When studying old galaxies, the amount of each element in them is compared with the Big Bang theory. The Big Bang model also matches the redshift observed in more distant galaxies. When light from distant galaxies reaches Earth, we see that it is greatly stretched. Its red color is more intense than it should be. This is the result of galaxies being distant from us. From numerous observations, we can conclude that in the universe, almost all objects are moving away from each other. In the universe's early stages, everything was closer together. The Big Bang theory also supports this. The most convincing evidence for this is the cosmic microwave background, which formed after the Big Bang. The theory about it was developed in 1948, and it was discovered in 1965. What James Webb discovered beyond our galaxy proves that commonly accepted theories need to be re-examined. The Cosmos UEBB program is about to launch soon. It is expected that with its help, we will see more early galaxies by expanding the observation area. This way, we will get a broader observation base, which will help us improve established models of star formation. James Webb could radically change history. Celestial objects are usually at enormous distances from each other, so enormous that a person who usually compares everything to earthly sizes can't even imagine it. What can we say if even light with its speed can't instantly reach a certain point? There is only one star system in the universe that we can consider close to us, and that's Alpha Centauri. It has been the focus of scientists' attention for several decades. So what makes it so special? What points can Earth's radio signals reach? As we know, many structured radio signals originate from Earth. Over time, they have managed to travel vast distances and reach quite distant star systems. Among them is, for example, the star Arcturus in the constellation Bootes. It is a red giant, 100 times brighter than the Sun, and is located about 36.7 light years from our planet. And that's far from the limit. The radio noise reached a distance of 65 light years. That's exactly the distance to the brightest star in the Taurus constellation, Aldebaran. Signals from us can also reach the so-called exoplanets, Gliese 667 cc, and ROS 128b, where living organisms could very well exist. Nevertheless, the closest to us is Alpha Centauri. Radio signals reach it faster, which means the first interstellar flight will be made to this star system. Alpha Centauri is a multiple star system that contains 3 stellar bodies: Alpha Centauri A, Alpha Centauri B, and Alpha Centauri C, also known as Proxima Centauri. At first glance, it may seem that there are actually 2 components, not 3. The thing is, 2 of the stars are very close to each other and seem to become a single entity. Together, they revolve around the center of mass, each on its own elliptical orbit. It takes them 80 years to do this. Their minimum distance is 11 astronomical units, while the maximum distance between them can be 35 astronomical units. Alpha Centauri Ea. Alpha Centauri A is considered the brightest star in this star system. It's even bigger than our Sun. The difference in mass is about 8%. Also, the amount of light energy emitted by Alpha Centauri A is 1.5 times greater than that of our star. Last year, studies were conducted in which Alpha Centauri A was observed using the infrared spectrum. As a result, traces of an object were discovered that, by its characteristics, resembled a planet. This body is many times larger than our planet. It's approximately 3 to 7 times the radius of Earth. The planet-like body is located at a distance of 1.1 astronomical units from Alpha Centauri A. Right now, we can't know for sure how accurate this data is. Additional research needs to be conducted for this. Alpha Centauri B. Now let's talk about the second star, Alpha Centauri B. Unlike the previous star, this one is smaller than the Sun. The mass of Alpha Centauri B is about 90% that of the Sun. In addition, the temperature on the surface of the star reaches 5,000 degrees Celsius. As a result, Alpha Centauri B has a more orange hue. At the same time, it is considered one of the brightest stars of this type. Also, flares of varying intensity are often recorded on the surface of the star. We haven't found any planets near this star that could support life. However, in the past decade, scientists have studied the object's trajectory over a period of 4 years, and they put forward a theory that there might be a planet not far from Alpha Centauri B, which would be about the same size as Earth. In 2015, it turned out that there was a mistake in the calculations. Therefore, the theory was not confirmed. Alpha Centauri C? But Alpha Centauri C has a more interesting story. It's a red dwarf whose mass is 88% less than the mass of the Sun. On the upper layers of the star, the temperature is just over 2,700 degrees Celsius. At the same time, it is Alpha Centauri C that is closest to our solar system. It is 4.25 light-years away from the Sun. Another name for the star is Proxima Centauri, which translates from Latin as the closest. It is worth noting that over time, the distance between Alpha Centauri C and the Sun is decreasing. Therefore, in thousands of years, it will be 1 light-year less. We can't observe the star from Earth precisely because of its small size. If Alpha Centauri A and Alpha Centauri B are at a short distance from each other, then Alpha Centauri C is separated from them by 13,000 astronomical units. Meanwhile, this value will decline over the years. As we mentioned earlier, it is unknown whether there are planets near Alpha Centauri A and Alpha Centauri B. The situation is different with the third star. We know for sure that there are 2 exoplanets near it, and there are theories about the existence of a third one. During research that used infrared radiation, scientists proposed a theory that the star might be surrounded by a ring made of dust. The first exoplanet, Proxima Centauri b. The first confirmed exoplanet discovered in 2016 is called Proxima Centauri b. Research using a spectrograph finally confirmed the existence of the planet in 2020. The distance to Alpha Centauri C is 0.05 astronomical units. The exoplanet completes a full orbit around its star in approximately 11 Earth days. The mass of Proxima Centauri b is about 10 to 20% greater than the mass of our planet. Its radius reaches 1.3 times the radius of Earth. Alpha Centauri C gives its exoplanet 1.5 times less solar energy than the Sun gives to Earth. On average, the surface of Proxima Centauri b reaches minus 39 degrees Celsius. From this, we can conclude that in certain parts of the object, there may even be some amount of unfrozen water. The exoplanet is most likely facing its star with only one side, which is called tidal locking. As a result, we have sharp temperature fluctuations, and the effect is only intensified by flares from Alpha Centauri C. This leads to the destruction of the exoplanet's atmosphere, which most likely doesn't even have a magnetic field. The second exoplanet is Proxima Centauri c. As we already mentioned, there is another exoplanet, Proxima Centauri c. Its existence was confirmed in 2020. The distance from the center to the exoplanet reaches 1.5 astronomical units. Proxima Centauri c completes a full orbit around the center in 5 years. We don't know the exact radius yet, and that's why we can't determine the class of the planet for now. Surface temperatures on Proxima Centauri c fall to minus 234 degrees. The reason for this could be the excessive distance from Alpha Centauri c. There is a theory that the exoplanet has rings. There is also a possibility that there is another planet in the system. Scientists came to this conclusion based on data from the Very Large Telescope. The distance from Alpha Centauri c is only 0.029 astronomical units. The planet would orbit its star in about 5 days. If such an object really exists, its surface would be heated up to 89 degrees Celsius. Nevertheless, the question of this planet's existence still remains open. How do you get to Alpha Centauri? For now, we can't make an interstellar flight to Alpha Centauri. Our spacecraft haven't yet reached the optimal speed for this. At the moment, we have the Breakthrough Starshot space program. As part of this program, 1 centimeter-sized probes are supposed to be sent to Alpha Centauri c for exploration. This can be accomplished before the year 2050. The time required will be about 2 decades. Data delivery will take significantly less, only 5 years. Finally, we still haven't reached such an amazing system as Alpha Centauri, even though it has repeatedly been the subject of research. However, Slowly but surely, we are moving toward our goal. And that means there will be one less mystery for us in space. Try to answer the question, what concerns space enthusiasts the most right now? That's right, habitable systems in the universe. There are many objects where living organisms could theoretically exist. However, they wouldn't resemble earthly beings. However, it's possible to find planets similar to Earth where life could exist. Today we'll talk about a special world whose existence we didn't know about for a long time, even though it wasn't that far from us. At the center of it all is the star Teegarden, discovered in 2003, which is a red dwarf located not far from the constellation Aries. The brightness of this object is 1,370 times lower than that of the main star of our planetary system. That's exactly why the star went undiscovered for so long. Therefore, even though the distance from Earth to Teegarden star is relatively small, 12.59 light years, we won't be able to see it without special instruments. The mass of the Sun is 91% greater than the mass of Teegarden star. In terms of size, if we compare it, say, to Jupiter, its radius is 5% smaller. It is worth noting that the level of gravitational forces on Teegarden star is low and is at the minimum level required to sustain internal thermonuclear reactions. As a result, the temperature of the object for this type is relatively low, 2,630 degrees Celsius. Since the star is a dwarf, its Goldilocks zone, in other words, its habitable zone, is not very wide. However, in 2019, during extensive research of this zone, scientists discovered 2 exoplanets. An interesting fact was that one of these exoplanets is actually located in an area that does not belong to the habitable zone of Teegarden star. This exoplanet was named Teegarden C. The planet was discovered by the Color Alta Observatory 3 years ago. They used the radial velocity method for this. The radius of this object's orbit is 0.045 astronomical units, and the orbit itself is as close as possible to a perfect circle. The exoplanet completes a full orbit around the center of the system in just over 11 days. According to calculations, Earth's mass is 11% less than that of Teegarden C. Its radius is also 3.5 times smaller than that of our exoplanet. Teegarden C has rather harsh conditions. Because of its distance from the main star, the amount of energy it receives is not very high. For comparison, Earth receives 63% more from the Sun. The average temperature on Teegarden C is usually no higher than minus 47 degrees Celsius. As you can understand, these figures are extremely low to support the normal functioning of potential living beings. Despite this, there is a theory that inside Teegarden C, just like on some of Jupiter's moons, there is salty water. In this place, the conditions might be better. The exoplanet that is located in the habitable zone is called Teegarden B. It has many similar characteristics to Earth. No other discovered object is as similar to our planet. Teegarden B's Earth Similarity Index is 0.95, while Earth's reference value is 1. The distance from the exoplanet to the star Teegarden is 0.025 astronomical units. Teegarden B completes a full orbit around its star in about 5 days. The orbit is also as close as possible to a perfect circle. This allows the exoplanet to remain within the habitable zone. As a result, the amount of radiation it receives is 15% higher than what Earth gets from the Sun. If we compare it to the mass of our planet, Earth's mass is 5% less than that of Teegarden B. We have reason to believe that the gravitational level on both planets is almost identical. It is quite possible that the internal structure of Teegarden B is also very similar to Earth's. Inside, there may be a metal core, surrounded by a molten mantle. The upper layer, compared to the other components, is relatively thin and consists mostly of various types of rock. Scientists suggest that the average temperature on Teegarden B reaches up to 28 degrees Celsius. On Earth, the average temperature is 14 degrees Celsius. Such figures open up the possibility for the existence of water oceans on Teegarden B. Moreover, their average temperature would provide optimal conditions for the existence of many organisms there. Despite all this, we do not know exactly what Teegarden B is made of, since the radial velocity method used to search for such exoplanets does not give us this information. If the atmosphere contains large amounts of carbon dioxide and methane, this will contribute to the formation of a greenhouse effect. If the dense clouds are mainly made up of water vapor, then the surface temperature drops, since such clouds reflect sunlight. Yes, indeed, Teegarden B and Earth have a lot in common. But at the same time, the exoplanet has a significant drawback. The planet is located quite close to its main star and is in tidal lock, meaning it always faces the star with only one side. This leads to the fact that on the surface of Teegarden B, temperatures in different areas can vary greatly. Also, the main star is classified as a red dwarf. Accordingly, light flares occur there quite often. The difference between luminosity levels because of this can reach up to 30%. This would make it more difficult for potential living beings to survive. Despite some negative factors, there is a high probability that living organisms could still exist on Teegarden B. Many microorganisms are quite resilient even to the harshest conditions. The upper layer of the water ocean could absorb incoming radiation, thus creating a protective layer. Sharp temperature fluctuations, which could also pose a problem for potential living organisms, can be mitigated by ocean currents. Taking these factors into account, simple organisms could very well emerge on Teegarden B. Who knows, maybe it has already happened. The system hasn't been fully explored yet, and there may be more shocking discoveries waiting for us. In the modern world, we make so many discoveries in such a short period of time. New and high-tech devices help with this. This increases the likelihood that sooner or later, we will eventually discover traces of extraterrestrial beings. If there are unknown worlds where intelligent life exists, then the inhabitants of those worlds definitely know that we, Earthlings, exist. Researchers say that the location of our planet is ideal for observing it from one of the planets of Teegarden. How much more do we still have to learn? Jupiter's satellite, Ganymede, is now considered the largest moon in our planetary system. Its diameter reaches 5,268 kilometers. This object was discovered by Galileo Galilei. This happened back in 1610. Galilei observed the night sky through a telescope he made himself and noticed several bright stars around. At first he thought there were 3, but then he noticed a 4th one. After some time, the scientists concluded that these objects around the gas giant were not stars, but satellites. They functioned in the same way as the moon. Before that, no such objects had been found in the solar system. This discovery served as proof of Copernicus's theory, the essence of which was that not all objects in the system revolve around the Earth. The discovery of Ganymede became a significant event for world science. The distance from Jupiter to Ganymede is about 1 million kilometers. Io and Europa are the closest to the gas giant. Jupiter, and therefore its moons, completes a full orbit around the Sun in 12 Earth years. Ganymede completes a full orbit around the gas giant in about 7 Earth days. Relative to Jupiter, Ganymede orbits at an angle and is constantly in tidal lock. In addition, the orbital period of this moon is related by a ratio of small whole numbers to the orbital periods of Io and Europa. That means these objects periodically exert gravitational influence on each other. This is called orbital resonance. During one revolution of Ganymede, Io makes 4 revolutions, while Europa makes 2. There has never been a case where all 3 moons lined up in a straight line. It is believed that Ganymede is 4.5 billion years old. This means that the moon existed in the early stages of the solar system's development. Ganymede has a rocky core inside with high temperatures, which still emits heat. Its temperature does not decrease, or rather it does so very, very slowly thanks to the fact that Ganymede is in tidal lock with its planet. The heat from the core is transferred to the icy mantle and then it rises to the upper layers. After the process of radioactive decay that occurs inside the core, iron is produced as well as iron sulfate. Based on these facts, it can be assumed that there is a liquid ocean inside Ganymede. It is also the only moon that has a magnetic field. It is located inside Jupiter's magnetic field due to the relatively small distance between Ganymede and the gas giant. When Jupiter's magnetic field changes, transformations also occur in Ganymede. Researchers have even recorded interference caused by changes in the moon's magnetosphere. Watch this short video where you can hear what the Juno spacecraft recorded. You might have noticed a shift to sharper frequencies at around the 25th second. At that moment, Juno moved from one magnetosphere to another. It wasn't just Juno that was gathering information about Ganymede's features. For example, Hubble detected a thin layer of atmosphere around the moon, which was mostly made up of oxygen. Water molecules from the ice on the surface, broken down by the sun's ionizing radiation, form the atmosphere. As a result of the breakdown of water molecules, hydrogen and oxygen are produced. Oxygen, unlike the lighter hydrogen, does not dissipate into space and exists in 2 forms, atomic and molecular. Atomic hydrogen is found at 3,000 kilometers altitude, while oxygen exists in the satellite's icy layer. Due to the low temperatures, molecular oxygen dissolves in the ice, so you won't find air bubbles in it like you do in Earth's ice. We still don't know everything, so research on Ganymede's atmosphere will continue. By analyzing the images of the moon that we have, we can say for sure that about 40% of Ganymede consists of older formations with many craters, and 60% is a younger type of terrain. The surface there vaguely resembles a patterned canvas. Because Ganymede's surface is covered with ice, the craters aren't as deep as on other objects. Based on photos with various relief formations, it becomes clear that when Ganymede was not yet in balance with its neighboring moons and was under especially strong gravitational influence from Jupiter, a huge number of tectonic processes took place on it. Canyons formed between the tectonic plates, and they were filled with water coming from the lower layers. The moon expanded due to the thermal influence of its core. As a result, an even greater number of fractures formed on the surface of Ganymede. The older terrain still needs to be studied because that way we can learn more about the nebula from which Ganymede originated. Take a look at this image of the moon. You can observe an interesting relief formation. It is called the Encke chain, Its length is about 151 kilometers. There are 13 closely spaced impact craters here. Scientists, during relatively short studies, found out that the formation of such a structure was caused by the Shoemaker-Levy comet. At some point, it changed its flight direction under the influence of Jupiter's gravity. The comet began to move around the gas giant, and with each pass it reduced its distance from its surface. Under the influence of Jupiter's forces, Shoemaker-Levy broke up into 21 fragments. Most likely, the comet came under the gravitational influence of Ganymede and crashed into its surface. That's how the Inky chain was formed. In the image, we see craters of different sizes. This may be due to the varying sizes of the comet fragments that formed. As we mentioned earlier, there is an ocean inside Ganymede. It is believed to be about 100 kilometers thick. Because the rocky elements interact with the salty water, simple organisms could exist in such an ocean. Since sunlight doesn't reach there, such organisms get their energy in alternative ways. At the same time, they need to be resistant to high pressure. Ganymede is not only the largest moon in our solar system, but also one of the most interesting space objects with many amazing features. The question of the presence of liquid water on the surface of the moon is especially fascinating. The search for liquid water in the universe helps scientists better understand the nature of space objects and gives us a chance that one day we might discover a habitable planet. Water ice can serve as a source of oxygen as well as drinking water, and the magnetosphere serves as protection from solar radiation, factors that could contribute to the colonization of Ganymede. However, there were also serious obstacles. For example, since the moon's atmosphere is low density and too thin, we would be exposed to intense radiation. How could we fix that? One possible option would be to place our modules along with the colonists not on the surface, but inside Ganymede, where the conditions are more comfortable. Nevertheless, these are just ideas that will not be implemented anytime soon. Several research probes have studied Ganymede. Besides Juno, there were also Pioneer 10, Pioneer 11, New Horizons, both Voyagers, and others. And the study of the moon will continue. We still have to find out more details about the internal structure of Ganymede, especially about the underground ocean, the physical characteristics of the upper ice layers, the magnetic field, and so on. Well, we'll be waiting for good news.